Let's start the continuing the proof. But before that, I want to recap something for the from the previous session. We speak of the matrix completion. There's a big matrix that we don't have all of the elements of the matrix. Now we have some unknown element in the matrix, and we had the example that is, for example, we have a list of the movies, and here is the name of the movie, and here is the name of the users, and some of the users rate the movies, but not all of the movies, and for example, they have some rating for some of the movies, and the rest is unknown. And with the matrix completion, it's the way that we can estimate the interest of the user and give them some suggestion for the next movies, because this user, for example, rates some movies and they didn't rate the rest, but we can find some code that shows the interest of the user, and based on that we can, for example, suggest them to watch some movies. Also, there is some other applications. For example, maybe you have a sensor network. It's a bunch of sensors that you can spread on the field, and because some issue in the energy, you cannot, for example, find you cannot measure the distance between all of the sensors between each two sensors, and you have only some distance between the sensors, and you're interested is to find all of the distance between the sensors. And it's another thing. For example, if we have for example, here the list of the sensors from 1 to, for example, M, and 1 to M, and we want to fit this matrix with all of the distance between the sensors, but for example, the sensors ones only can measure the distance between itself and 3 sensors, and there's, for example, 10, 15, and 20 with some 3 sensors, and the rest is unknown. And the objective is to, for example, receive these distances and estimate what is the distance, for example, between one and the rest of the sensors. Yeah, it's one of the application of matrix completion. It can, for example, estimate the distance, because if we have, there is a good chance to, for example, there is, for example, if we have, for example, tree, something like this, we know exact point of this tree, and based on this, we can, for example, make a map of all of the distance between the sensors. It's one of the applications.
Who proposed this?
I read it in the introduction of a paper for matrix completion with noise by Candace. It's one of the application, and the others is, for example, it's not exactly 3 of them. It's, for example, sum of the distance and try to find the others, not exactly 3.
Actually, if it's 1D, I can't agree with her. If 2D, how
it's really, I didn't go through the detail of that, but it's one of them. And in the previous session, we reviewed some of the properties that we can use for the proof of the others. For example, we define the minimum rank of the matrix. For example, if we have a matrix, let's say 1, 2, 3, 4, 5, 6, and the minimum rank of this matrix is 2. If you, for example, count the number of the column and number of the rows, and which one is the minimum, the rank of the matrix is the minimum number of size of the rows or columns. And based on this, we review some of the properties and start to prove of this definition that if, for example, two matrices are, if the matrix M and the of B1 till Bn are equivalent, then the minimum rank of M is the minimum rank of each submatrix in the of B1 to Bn. That the definition is this one. The diag of B1 to Bn, it's the matrix that the diagonal of the matrix are this submatrix, and the rest is unknown. And we start to prove, and in the first step we reach to this one, and with this assumption that if we have the matrix that it has only two submatrix A and B, and minimum rank of the and the rank of the completion of A is equal to a small a, and the rank of the completion of the B is B. We have the maximum of the A and the minimum rank of the matrix B is between maximum of A and B and the minimum rank of the U diagonal of A and B. And we start to prove, and again we assume that the completion of the matrix A has, for example, A columns because of the rank of that, and we use this fact, this assumption that, for example, if A is bigger than B, we can do the completion on the matrix A. For example, for all of the matrix, the columns from AI completed and unknown, we can complete the matrix by AI and BI. It's for all of the AI because the number of AI is bigger than number of the BI, and if for the BI, for the part that's we have the B, we can do the completion by exchanging the AI but by unknown, and for the part of AI that we don't have any BI because the number of the BI is less than AI, we fill 0, and again we know if the minimum rank of the completion of the rank of the completed matrix A is small a, the rest of the columns is only, for example, we have the A column that is unique, and the rest is the some linear combination of this A matrix. Because of this, we can use this fact for the rest column of the AI. We can use this fact that we can, if we exchange the value of unknown with this matrix, we can do the row exchanging or add or subtract the columns, and we can have the set of the columns as, for example, it's the unique unique columns in the on diagonal of A and B, which these columns are A1 till B1 till BB, and AB plus 1 0 till A0 A0, and this shows the minimum rank of this one is equal to A, because we have only A column that is unique, okay, and this A is maximum of A and B. Because of this, the minimum rank of on diagonal A completed and B is less than A, which this A is less or equal to A, which is equal to maximum of A and B. And we have here the minimum rank of this is bigger than this, and if we replace this value with max of A and B, the minimum rank of A must be equal to maximum of A and B. Okay, and here we have the, for example, minimum rank of the A is maximum of the rank of the each component in the on diagonal matrix. From this theorem, that it's, let me keep the numbers of the theorem as 3.1. We can use this fact that if A has been completed by A bar, and small a is the rank of A bar, if the A is bigger than a matrix B, which can completed by B equal to rank of B. If we have these two matrices in a on diagonal matrix, it's not necessary. We don't need to, for example, do the completion on the B, because the rank of the A, B, it's only depend on the A, and because of this we can do the completion on the B. It's in the arbitrary way, and it's not necessary, for example, to find the minimum of that, because the part of A is important, and the result of this part create the minimum rank of the original matrix M, which is equivalent to this one. Let's improve this theorem to use it for finding the low rank matrix. But before that, there is after here we call the BI's as a cluster, and we use this cluster to decompose the matrix and reach to the minimum rank available for the completion of a matrix.
Excuse me. What's the lowest rank of the matrix? Is it 0 or is it 1?
The rank of the matrix is a natural number between, for example, 1 to something, because we suppose that, for example, the matrix at least one element, and this number can be any number between 1 and infinity. But when we have a very big matrix and with some unknown, as I will explain next, we can, for example, ignore some columns and some rows which don't affect the rank of the matrix, and start to shaking the matrix and find some cores and do the reverse process to find the relation between and to find the value of unknown elements in the matrix. Let me explain the neighborhood in the matrix. For example, in the ordinary case, when we speak neighbor of the one element, we use, for example, some numbers in the around of that. But here, when we use the neighbor of one element, we use, for example, if it's m by n, the number of neighbor of this element is m plus n minus 2, and this is the number of one element, and we can, for example, count the unknown number in the neighbor of each point, and based on that we can estimate, for example, how many clusters it is possible in this matrix, and based on that, when we reach to that amount of the cluster, we can, for example, stop the process. Let's start the decomposition algorithm. For the decomposition algorithm, we have a junk-free matrix. We explained that the junk row or junk column is the column that's the minimum rank of that is equal to 0. Because of this, before starting the process of decomposition, we delete all of the rows or columns that's they are the junk. It means they are 0 or unknown.
So you said that the lowest rank is 1. Now is the rank of the junk column, or
The
has
minimum
zero
rank of
because,
the
because that one is nothing, just remove it.
yeah.
There's no element there.
And here we want to, for example, create a set of rows and columns which are in the one cluster. For example, if we have a big matrix, we can, for example, we can select first column, and we have a two set of columns and set of the rows. And then, for example, if we select one column, we put this number in this set, for example, J1, and we mark this column as, for example, this column belongs to the, for example, the cluster 1, and we try to find which column is similar to this column. If we have a create one column similar to this one. In this column we have some noun element and some unknown element. We try to find a similar element to this column. It means in the same look, if for example in this location there is some unknown, we try to find which column it's exactly in this point it has some unknown, and based on this we try to, for example, mark those columns and move it here. For example, this is the column, for example. And after that we start, for example, to select the rows. For example, there is some rows again, and we put the I1 to IN here. And after finishing this process, we have, for example, a matrix with these elements. They are unknown, and the rest of these elements here with the noun elements here create the smallest matrix, okay, because they are unknown, and we have something here that all of the point is unknown, and we use this one as our clusters B1 T B N here. Okay?
So for this matrix, all the elements is unknown, right?
No, all elements known.
Known.
Yeah. Okay. Because we marked which one is unknown, and we find the similar between them and create a matrix which all of the element is the rest of this column. Maybe there is some unknown, but no, all of the elements is known. Because if there is some unknown, this column is not similar to this column, and it's create another column.
You remove the column or row, or not just remove that unknown elements?
No. We select all of the columns and
remove
rows and create another matrix.
No. I mean for the creating that noun was matrix.
Okay.
Just for that, for the first matrix, just remove the column
Okay.
and row, or no, just remove the.
Let me show with the example. For example, if in this column we have unknown here, here, and here, in all of this matrix, all of these columns, we have unknown here, here, here. And this one create a junk row.
Yeah.
Okay, because of this, we don't need this junk row.
You can just
And
remove the junk row.
Yeah,
Okay.
we can remove the junk row and put the column here.
Yeah, because if you cannot, you just remove the elements.
Yeah.
Just.
And we can do the columns and row by row and column by column, and we can find the clusters of the matrix. Okay. Okay, and we know if we find this sub-matrix, we don't need to do a matrix completion on the big matrix, because we know the maximum rank of this big matrix is equal to maximum rank of each of these small matrices. Okay, based on this theorem, if we can find some sub-matrices, the minimum rank of this big matrix is equal to maximum of one of these. And finding the minimum rank of this cluster is easier than find the big one here. And there is a definition, because you know it's not possible always to find a clear cluster, something like this, and there is always some rows and some columns that it cannot for example, separate the good shape matrices. There is a definition of zero. I don't know what's the meaning of that, but we define zero of a column U and matrix A is equal to 1 if for completion of for all U completed and A completed belongs to S of UA is equal to minimum rank of UA, then U equal to 0, U completed equal to 0, and otherwise 0, U and A is equal to 0. For example, if we have 0 and 1, this one is equal to 1, because here it's important what is the value of this unknown. If it's equal to 1, the minimum rank of the big matrix of 0, 1, for example 1, 1, it's 2. But if it's 0, the minimum rank of this matrix is only 1, because this one is a junk, and the minimum rank of this one is 1. Okay? And 0, another example, 0 of, for example, 0, 1 is equal to 0, because here is not important. If this one is 0 or non-zero, the minimum rank of this is only, it has only 1 row or 1 column, because this one is a junk. Okay, because of this column is 0. We call it the function 0 on these two matrices is equal to 0, because here it's not important what's the value of the unknown. And
why the first one is equal to 1?
Because here this one is not 0.
Because it's 0, 1,
Yeah,
0, 1.
because if it is a 0, the rank of the result is 1. But if it's not 0, the rank of it is bigger than 1. Okay? But here, if it's 0, the rank is 1. And it's non-zero, again, rank is 1. And shows the 0 of this function is true, and 0 of this function is, this one is false, and this one is true. This one must be 0, but this one is not. We can do arbitrary completion on these two matrices, and doesn't matter what's the number, what's the value of unknown here. But here it's important.
What does 0 stand for?
0 is the function. 0 of these two matrices, it's, for example, function if 0 of these two is equal to 0. It means here is not necessary to be 0. It can be any number. And the minimum rank of these two, for example, minimum rank of 0, if I put any number here, for example 5, this minimum rank of this matrix is equal to this one. But here, minimum rank of, for example, 0, 0, and 1, 1 is equal to 1. But minimum rank of 0, for example, 2, 1, 1 is equal to 2. Because here we have 1 junk and we can remove it and the rank is 1. But here we cannot and the rank is 2. And here this one is already junk and the rank is 1, and this value of unknown here cannot change the minimum rank of the matrix.
The middle zero. The middle.
The middle. The second one?
Yeah,
This one.
Yeah. If consider element saying maybe equal 1.
Yeah, it's equal to 1. It can be 0, 0, 1, 1. And this row is junk, and the minimum rank is equal to 1.
Yeah.
Okay, sure.
What was this?
The 0 of this,
You mean 0 function on this element?
these two elements together.
Okay.
This one is the column, and this one is the matrix.
Column matrix and is equal 0 after the function.
Yeah, the result of this function is 0.
All 0. All the matrix is 0.
No,
Okay.
it's a function. Yeah, let me write it down again. Okay, for example,
Maybe just read
0.
the definition again, like the
Definition.
This definition of here.
This?
No.
The definition is here. 0 of u and a is equal to 1 if the rank, the value of unknown value in the u affect the rank of the matrix, minimum rank of the intersection, not intersection, in the union of two matrices. Yeah, but
definition.
yeah, it's by definition. This is a function.
Oh, you define definition.
Yeah.
Oh, yeah.
Okay.
Thank you.
And okay, and we have a theorem that
Actually, I want to comment that it's not just, it doesn't matter, it's not just, it matters what u should be, but it's really when 0 is 1 for that function, then u has to be equal to 0 if you want to get minimum rank from that definition. What did you just
Okay.
say was that?
yeah, we need this one and this one. In this one, it's the 0
For example, this
of
one
this
is equal to
one.
1.
is equal to 1.
That actually, if you want to achieve the minimum rank for this, the whole matrix, I
Yeah.
pack together,
It's exactly true.
that
It's
has
definitely true.
to be.
But
then-
we are interested to find some unknown elements that we don't have to spend some time to find what is the exact number of this. We want to, for example, throw out this type of the unknown, something like, for example, 0, 0, 1 unknown. This type of unknown doesn't matter what's that. We can, for example, put some arbitrary number and fill it with some number, and the rest of the minimum rank is the same as the before. But here it's important, and we must keep this type of the unknown and fill it later, because it needs to more computation and find what is the relation here between the rows and the columns.
Yeah, anyway, just continue.
Okay. And there is a theorem that the proof of that is similar to the this one, 3.1, 3.1. This, if m is equal to, for example, v1 to vn of b1 bn, where the bi's are the matrices and vi, tvn are only they create a not junk column. It means V1, Vn, the minimum rank of this one is not equal to 0. The minimum rank of M is equal to maximum over I of minimum rank of Vi plus 0 of Vi. If the proof of this is similar to this, again we can split the column and mix the Vi with Bi with some column exchanging and adding some columns that are the summation of the, for example, for the first one, we can split the column V to the to Vi and the rest, and put Vi with Bi, and put some summation of the rest of the Bi's here, and again we can find the what is the, for example, limit of the minimum rank, and the minimum rank again is between, for example, maximum of maximum of, for example, again A and B, and the minimum rank of this minimum rank of minimum of this part plus it's depend on the what is the value of Vi. We can prove that here if the 0 of Vi and Bi is equal to 0, we don't need a 1 here, but if there is some dependency between the Vi and Bi, we must add 1 here, and it's make the again this equality to something we proved before, that the minimum rank of the minimum rank of the M is maximum of this one plus 0 of Vi. And based on this theorem, we can use this one for completing, for example, the matrices that they have, for example, some type of the unknown element, something like A. And if we use this fact, we can divide this matrix to the matrix A, U, and matrix V, B, X, U, D, and again we can decompose this matrix as this big A, U, and here V, B, X, and U, D. if we have this matrix, we can use this fact and assume, for example, this one is one column, which, excuse me, this one is one row, and we try to split. We can move A here and split A and the rest here, A and the rest here, and the part of B unknown. Maybe I can write it down as. I can change the order of the rows, and we can have U, A, V, unknown, yes, unknown, B, unknown, X, Y, E, and we can assume this one is the one of this V that we assume that, and we can divide here. There is a one cluster here and another cluster here. Okay, and again we can use this fact and try to complete this part and this part separately. And again in this part, for example, I can X, Y, B, unknown, D, and this one is again a new V, and again I can split from here, and this one is a new cluster with this one. Okay, and you can see here, for example, Y, D, because middle is only junk. Okay, because all of this is unknown, and YD is another cluster of this matrix. Okay, let's start trimming process. It's the end of presentation. This process led us to decompose a big matrix to some small matrices and try to do the completion on a small part, and do the reverse process to complete the whole matrix. For the trimming, there is a lemma with the minimum rank of Vm is equal to minimum rank of M. If M belongs to M complete S of M, and columns of M completed M, the intersection of the columns of completed M, and the S of V, there's no intersection between these two. And it's easy proof because based on the number 2 and number 5, if we mix these two and use the this fact that if there is no intersection between these two, the minimum rank of these two is equal to minimum rank, V and M is equal to minimum rank of M. And based on this, there's a theorem that it can be proved by this lemma, which is if we have MDI, which is DI column define this definition. We have another definition of the donor. I think we forgot to mention that. We define V is a donor for W if V and W are in the same size and all the unknown position of V are the same of unknown position of V of W. Okay. If the unknown position of V, for example, is here and here, and the says all of the unknown position of V are also unknown in W. It means if this one is V, this one is W, this one is donor for this one. Because all of the location in the V, it's let me take a check. All of the unknown position of the V
Unknown to
in the W. And this is the sign of donor. V is donor of W. And if there is also there is some cases maybe V is donor for W and W is donor of V because V and W are comparable. And this definition is equal to
for comparable is mean that both of them unknown is the same position.
in the same location, in position. Yes. All of the unknown of V is and for example here if V is donor for W, the WV by exchanging the row and columns can be equal to R completed, D completed, N and unknown. If we merge these two matrices and we can find some matrices in this shape, we can say V is donor for W. Let's back to the trimming algorithm. In the trimming algorithm, we have MDI, which is one of the columns of M, and the donor and the donor of a vector V for I between 1 and after row exchanging we have V MD1 R, small r, belong to columns of decompleted. R is one of the columns of decompleted. Then the minimum rank of V M is equal to minimum rank of N. Okay. If we add one column to the T part of the whole matrix, T columns of the whole matrix, and we can do the rows exchanging and find the sum matrix in this shape, which R, D, R complete, D complete, N, and this part is unknown. If R is one of the columns of D completed, then the V cannot change the minimum rank of M, and we can delete this column. Okay, and it's easy. It's easy to, for example, doing this this fact on this matrix for example, if we have we define some columns between not between columns MDR D1 to MDT. Applying this lemma, and it shows this extra column cannot change the minimum rank of the matrix. And based on this fact, we can do the trimming process on the big matrix. We start column by column if we have a big matrix. And we start column by column and use this theorem to find some rows which cannot change the minimum rank of the matrix, and try to mark these rows and keep the record of the column. For example, if we find this column cannot change the minimum rank, we mark this one, and you try to apply the others column, and we have the list of the columns and rows, and we keep the order of, for example, this one, if it's A, we give A1T AN and B1T BN, and we do this process until we cannot do anymore, and there is no column that has this that we can apply this theorem on that, and start to doing on the rows, and after doing on the rows again repeat this two, and we create a small matrix, and after that we start to do the reverse process. In the reverse process, for example, if the last column is AN and we want to add the AN to the matrix, we check which this new column, if we add to the matrix, is there any column that, for example, can be applied again this one, and we try to do the reverse process. In the sum part again, we have the diagonalization on the matrix, and we can, for example, find some component that is totally complete in the matrix and do the completion for the all of the matrix. And we know if we find the, for example, minimum rank of the one of the component, the minimum rank of the big matrix is equal to minimum rank of the maximum of one of its components. Okay. Any question?
Stop the tape.